All right, here's our first theorem of today. There we are. The theorem is, so where do we leave off? We've been working our way through, we're getting better and better at sequences, proving theorems about sequences, all kinds of fun stuff. So today, our first theorem is that limits are unique. If you have a limit, there can only be one limit. Okay, limits are unique. Limits are unique. How would we say that in mathematics? Sadly.
I mean, I'm not going to be like too formal with it, but basically, if you have like a limit L and a limit M for like the same function, then L has to be 12.
Right. So assume, let's call this A to L. Apparently, I called it A to L because that A converges to L, and assume A to M, which is that the sequence A converges to M, then the goal will be to show L equals M. Okay? How do you prove something like this?
Where you prove the word is that it's to L equals to equal to M and then show contradiction.
Exactly. Exactly. In order to get started, where am I supposed to get an epsilon from? Well, if L and M are different, right? The key idea, if you think about what this is saying, here's your sequence A, and it's saying it has a limit L, and it also has a limit M. Well, if L and M are different, then we're going to be in trouble, right? So we have to be able to have a way of saying, we're going to argue by contradiction. Okay? So idea, argue by contradiction, argue by contradiction. What is that called in lean? That's this new, the new ones are yellow. The new tactics are yellow. The new theorem names are yellow. It's called by contra. Okay. So in lean, what you do is you say by contra, what it's going to do, it's going to look at the goal. It's going to negate the goal and add that as a hypothesis and change the goal to false. Okay. So this will add a goal, add a hypothesis. Now, what's that hypothesis called? You have to give it a name. It's a dummy variable. Okay. So what you say is by contra H or LLNEM or something. By contra LNEM. L is not equal to M. Whatever you want to call it. Okay. It's going to add a hypothesis LNEM, which is the negation of the goal, of the current goal. L. So it's not, what it's actually going to do is say it's not the case that L equals M. And change the goal and change the goal to false, as we already said. Okay, that's what by contra L does. Do I have to teach you anything else before we go? Yes, there's one more thing we're going to need. We're going to need it right away. The thing that we're going to need next, so new theorem name. And the only reason I have to teach you theorem names is because there should be a tactic that handles it, and I'm working on it, but these things aren't so easy. Abs pos of non-zero. So the new theorem name is abs pos of non-zero. Bound should do this, but it doesn't. Can you guess by the name what it does? The theorem says exactly the positivity of the absolute value of something if you have a hypothesis. So I'll write it as an implication. If you have that x is not equal to 0, then you can prove that the absolute value of x is positive. Okay, abs pos of non-neg. Non-zero, not non-neg, non-zero. Abs pos of non-zero. So we need a strict inequality on L, on the difference between L and M from there. Okay, does that make sense?
Before, like when we had to prove that something that didn't converge, like we would change the goal to be like an implication and assume the hypothesis. Is this just what like by contra does for us?
In a sense, yes. By contra is a combination of several other things, and we're going to learn what some of those things are. But when you want to argue by contradiction, the lean version for it is by contra, and then you give it a name. Okay, let's start the proof. Well, let's work on the idea of the proof. What's the idea of the proof? If they're indeed different, then what? Jeffrey. Exactly. So the idea is if L is not equal to M, set epsilon equal to like L minus M over 2, and you're going to have a problem, or over 4 or something if you want to be, there's no reason to go anything other than over 2. And the problem is eventually AN is going to be, well, all eventual values of AN will be within epsilon of M, and they'll also be within some other eventuality, they'll eventually be all within epsilon of L, and the distance between M and L is more than L minus M over 2. There's an over here somewhere, over 2 plus itself. Okay, so the idea is very simple. Let's execute it. Everybody, that makes sense to everybody? Let's execute it. First, the natural language. So we argue by contradiction, so proof. By contradiction. Oh my God, what is going on? I'm not getting enough sleep. By contra, that's why it's called by contra, since I can't spell the rest of the word. Come on, a contradiction, there we go. By contradiction, we can assume a hypothesis that, what do you want to call it? H or L not equal to M or what? H, good. Assume, and we'll call this hypothesis H, that L is not equal to M. Okay, I can't use, that's not a proof that this is true. Then, let's call it like this. Then L minus M is not equal to 0. And hence, this is going to use abs pos of non-zero. Abs pos of non-zero. Bless you. What do we get? We get that 0 is less than the absolute value of L minus M. So far, so good. Clearly, also, we have that 0 is less than L minus M over 2. Why do I keep M, close the absolute value, then a bar, there we go. And let's call this, what do you want to call this? Back, bless you. F1, great. Yeah, F1. Okay. So now what? So this is what we want to use for our epsilon. Where do we stick the epsilon? Joe, you got an idea?
Specialize both our hypotheses to the epsilon.
Perfect. Yeah, so our two hypotheses are A to L and A to M. So we specialize A to L and specialize A to M with epsilon replaced by L minus M over 2. And why is it positive? F1. This will turn, so this line makes A to L, then A to L becomes, there exists an N, let's call it N1, so that for all N greater than N1, yada, yada, AN minus L is less than epsilon. And there's also an A to M, which says there exists some N2, so that for all N greater than N2, yada, yada. You agree that those are the new hypotheses? So now what? Suhas. Yep. If you have an exist statement in a hypothesis, you choose it. Choose N1 and maybe HN1 using A to L. What does the hypothesis HN1 now say? Beautiful. AN minus L is less than epsilon. And then we're also going to choose N2 with HN2 using A to M. That'll give us hypothesis N2, which says for all N greater than N2, AN minus M is less than epsilon, but it's not epsilon. It's L minus M over 2. And again, here, the same L minus M over 2. Okay. Those are our two hypotheses now, HN1 and HN2. Now what? I've called on Daniel, I've called on Joe, Akil. Used. The goal is false. Jeffrey.
I guess first have to do like have M plus F2 greater than N1.
Excellent. What's the idea? What are you going to use for little n? You don't have any natural numbers floating around, except N1 and big N1 and big N2. So Jeffrey, your idea is we're going to do the have, but that is exactly what the next command will be. But why are you doing that have? What are you thinking? Exactly. The idea, okay, so the idea at this point, idea is that use n is equal to n1 plus n2. I don't mean use in the technical sense. I mean, that's where we're going to set n1 and n2 to. So our next line will be have, what is this, fact 2 or something? We only have a fact 1 so far. Fact 2 is that n 1 is less than or equal to n1 plus n2, and this is by bound. Similarly, we'll have fact 3, which is that n2 is also less than or equal to this. And the reason we're doing this is because we want to specialize h and 1 to what value of n? N1, big N1 plus N2. And why is it we can only get the conclusion with this condition, F2. So I feed it F2. So now I'm keeping track of the goal state. HN1 says AN minus L is less than L minus M over 2. And now specialize HN2 to the same sum. And now with F3, because we need to know that N2 is less than N1 plus N2. And that makes HN2 say not N, actually not N, but N1 plus N2 minus L. And same thing here. This is N1 plus N2 minus M is also less than the same epsilon. Everybody see that? Okay, now what? Jeffrey sees what to do. Sean.
I think like our eventual contradiction is going to be L minus M instead of L minus.
Beautiful. Yeah, let's think. How are we going to do this? So the idea is to get a contradiction with L minus M, but L minus M is equal to what? Sean?
Minus AN minus, or AN 1 plus N2 minus L, and then AN plus N2 minus M.
Exactly right. We're going to add and subtract AN minus 2. Then apply. Yeah, abs-add. What is it called in English? The triangle inequality. Okay, the triangle inequality says this. N1 plus N2 plus AN1 plus N2 is less than M. This is by abs-add triangle inequality. Okay, so in a dot meaning continue this, or let me write it the way I hope we'll eventually be able to write it, which is just underscore, the same thing. And now, what's this bounded by? Well, now we need a separate little fact. I already know that AN1 plus N2 minus M is small enough. This thing is almost what I need it to be. Jeffrey. Yes, let's have another, this is going to be maybe F4, which is, yeah, we have to do it in 2 stages. So L1 minus AN1 plus N2 is equal to the negative of AN1 plus N2 minus L. And that's just because of ring normal form. And then have F5, which is that the absolute value of negative an1 plus n2, there's no reason to have parenthesis there, is equal to the same thing with just an1 plus n2 minus L. And that's by apply abs neg. And now I think we have everything we need, because this is less than L over 2. Let's give these names. So this was F4, F5. I guess this should be called F6, will be a half. F7 will be another half. And then linearith. So if we combine F6, linearith using F6, sir, F6, bless you, F7. So L minus M, we added and subtracted. Then we broke it up like this. This is bounded because of F3. This is equal to this thing. So that's F4 and F5, F4 and F5. And why is this bounded by L over M over 2? That's, oh, I'm sorry. That's called HN1 and HN2. What did I call it? F3. No, it's not F3. It's HN1 and HN2. HN2, I guess, and HN1. The order doesn't matter well. And we're done. Okay? Make sense? Limits are unique. Let's see if it works. Okay, so I'll pull this over. And I guess that's as far as I can take it. Okay, and then I just write some nonsense, apply. It says I don't know what to apply. All right, so our proof is, here's our proof. Here's the idea of the proof. We're going to start right here, by contra, or right here, by contradiction, by contra, and we want to call this H. And look at what happened. We have a new hypothesis that it's not true that L is equal to M, and the goal has become false. Great. Next, L is not equal to M, so we're going to have to set that separately. Have F, I guess it's F0. Let's try to keep the numbering the same. Have F0 that L minus M is not equal to 0 by bound. Let's hope bound does it. And again, we have to check in editor mode that, oh my God, did I break it because I made it too small? Let's try that again. Editor mode. Nope. Editor mode. Where's the text?
Wrong.
Oh God. All right, we're working out the kinks. Let's hope it, let's just keep going. I think it's okay. We'll find out soon enough if it is or not. Oh, it crashed, that's why. God, okay, I'm not gonna do that anymore. By contra H. We're at the beginning. Nope. Reload. Reload from the beginning. You can't, don't give me any more by contras, because that's going to be bad, because now I don't know what's going on. Let's go. Okay, let's say that bound worked. Okay, so we have this F0, and now what I want to do is do we give a name to this thing? We didn't. So F0 prime is the fact that 0 is less than absolute value of L minus M, and that's by apply our new theorem, abs pos of non-zero. And what's the non-zeroness? F0. F0 is the non-zeroness. Okay, so now we have this fact F0 prime that L minus M in absolute value is strictly positive. We needed that because now we're going to have, we said we call it F1, which is that 0 is less than L minus M over 2. And that should work by bound or linearith. I think bound will do it. Okay, we have that fact. That was F1. Now we're going to specialize. Remember, this is for all epsilon, so that's what we're going to use for our epsilon. So let's specialize A to L with epsilon replaced by L minus M over 2. And the fact that it's positive is F1, exactly as we just did. And copy and paste is your friend. Okay, we have that there exists an N1 for A to L, and there exists an N2, except Lean didn't let us do our dummy variables, but when we choose them, we get to name them. So choose N1, HN1 using A to L. choose N2, HN2 using A to M. All right, we have our N1 and our N2. And the idea is any little n greater than N1 and greater than N2 will work. Which little n are we going to apply this to? Big N1 plus big N2. Okay, so let's record this fact. What do we call it? F2, that N1 is less than N1 plus N2. And let's record F3 that N2 is less than, please, N1 plus N2, also by bound. And now we can specialize HN1 to N equal to N1 plus N2. And the reason we can do that is F2. Everybody with me? Am I going too fast? Make sense? That's what HN1 has become. It's that A N1 minus L is less than L minus M over 2. And now I'm going to do the same thing with N2 and F3. And now HN2 has become this difference. Good? We have those differences. Now we just have to record a whole bunch of things. Let's record F6 for some reason. They don't have to be in order. F6 is that L minus M is equal to L minus A of N1 plus N2 plus A of N1 plus N2 minus M. And that's all true inside the absolute values, and that's by ring. Am I going too fast? No. Everybody's following along? Uh-oh. Whoops. Not ring parenthesis NF, but ring underscore NF. Okay, we've got that equality. That's F6. F7 is that this left-hand side, which I'm going to copy, have F7, which is the left-hand side, is less than or equal to the same thing, but with absolute values stuck in. And that's because of applying abs add, the triangle inequality. That's our inequality F7. Good. And now let's have F4. So this AN minus M is already good because it's exactly what we have in HN2. But this one we have to turn around. Again, there should be better automation for this. The people who I teach 10 years from now, next time I teach this course, will be very happy that you suffered for all of this, for it to get right. Okay, so this thing is equal to the same thing, except I'm going to put pull the minus sign out front and subtract L, and that's simply by ring, just rearranging algebraic expressions. That's called F4. And now this thing, I can drop the minus sign. Have, what do we call that? F5 is the fact that I can drop the minus sign. And that's by apply abs neg. Thank you. All right, and then Linnerith. Linnerith, F6, F7, HN2, F4, F5, and HN1. Any questions? Cool. Moving right along.
I think underneath, like,
Please.
So when you write the theorems that you use, like abs at non-zero or whatever you do for yourself, or is it defined in the main game server?
No, I do them myself.
So then, is it like, could one of us open the beyond to solve that absolute value thing so that you don't have to do all the steps?
That would be great. The solution to the absolute value thing, well, the solution to the right solution to the absolute value thing is metaprogramming. Better metaprogramming. The bound should just know to do that. You can write a theorem for it. I mean, there sort of is a theorem. In fact, there is a theorem. And I don't know why I taught you two things instead of teaching you the one theorem that does it. There is a theorem that says if you have the absolute value of A minus B, it is the same thing as the absolute value of B minus A. I could have just taught you that, and instead I don't know. I'm tired. Let's go. Yeah, all of these things, there's a better way to do. But as long as we're learning the subject and we're learning it with clarity and precision, I'm happy. Let's go. Next. Okay, back to the game. What do we got? Eventually greater than or equal to half the limit. All right, this you can work on your own. Let's take 5 minutes and everybody come up with a proof of this fact. Let's make this the quiz. This is a good quiz. This is something we should be able to do. Okay, so we have a sequence A. It goes to L, and L is not 0. And I want to know that eventually means there's some capital N, so that once little n is bigger than that capital N, for all sufficiently large values of little n, the absolute value of A of n is at least L over 2. Absolute value of L over 2. Let's, before I send you on a formal proof of this, let's just think about this in, oh, come on. Let's just think about this in natural language, what's going on. So theorem 2, next theorem. The theorem is called, did we give it a name? Yes. Bless you. It's called eventually, so bless you. You're eventually greater than or equal to half the limit. That's the name of this theorem. Maybe that's a terrible name, but you're welcome to PR a better one. Our objects are A. A is a sequence, and L is a real number. We have the assumption A to L, which is that A goes to L, seq lim. We have the assumption that L is not equal to 0. And our goal is to show that eventually, okay, there's some capital N, so that for all little n greater than capital N, this is also known as colloquially, eventually. Eventually what? A of n in absolute value is at least L over 2. Okay, so in a picture, what's the situation? You have some sequence an, it's doing whatever. Let's say it's doing this. And you have some number L. I didn't say if it was positive or negative. I just know that it's not 0. Is this theorem true if L is 0? If L is 0, you can go, 1 over n, negative 1 over n. A half, negative a third, a quarter, negative a fifth, and so on. And that sequence will approach 0, but sometimes it's positive and sometimes it's negative. Okay, let me write a little note. If L is not equal to 0, then the theorem is false. So it's a necessary condition. What's that condition called? LNE0 is necessary. LNE0 is a necessary condition. Why is look at the sequence 1, negative a half, a third, negative a quarter, and so on. And actually it's not true. it's not necessary. It's always true, but I haven't taught you by cases yet, and so we're yeah. So forget it. So forget what if I was going to tell you something about strict, yeah. In my mind it was a strict inequality, but here I have a greater than or equal to. Okay, if it was a strict inequality, if I'll finish the thought, and we wanted and the goal was L over 2 strictly less than an. No, then, well, yeah. So actually this would not be true, not for this sequence, but for the sequence of all zeros. Okay, you get the point. You have to be careful about conditions.
Hey, well, what if you have like the sequence, like if L was not 0, if you have a sequence of all L's, what's that? Oh no, it doesn't. Okay, I get it.
Yeah. That's that. Yeah, if you had the sequence of all L's, exactly. If I had a strict inequality, I'd be okay. If I have if L is 0, then a strict inequality would not be okay. All right, so you get the point. So L is down here. We know that A gets closer and closer to L. And so how about the absolute value of A? I claim that will be eventually, there's some value of n so that you're always above absolute value of L over 2. You have 5 minutes. It's for you on paper, whatever you prefer. I would write out an informal proof that explains the ideas, but as I'm writing the informal proof, I'm also thinking about how the formal one will go. I want to give you a chance to really think this through on your own and test whether you can do it. What's the idea? Does everybody, don't tell me. Does everybody have the idea? Everybody have something in mind? Good. Nobody's stuck. If anybody wants a hint, just let me know. I'll come around. And give me a thumbs up if you got it already.
We only need nothing.
Say it again.
We only need nothing.
Whatever you prefer. It's for you. Yeah. You might want more paper though. A little half sheet.
Rather on the class, please.
Do you not have paper?
I didn't read them because I usually write on my head stylus.
Okay, we have to bring paper every class. Yeah, bring paper every class. You can borrow a sheet of paper from someone. I guess not borrow. Not give you back. Yeah, I think you want some paper because you need to be able to think. You can't think on something this small.
Thanks.
Thanks, guys. Yeah, make sure you bring paper every single time. Would it help if you worked in groups? You gonna be able to talk to your neighbor? Be my guest. I will say that this is exactly the kind of thing that's completely fair game for an exam. So you want to practice coming up with your own solution. It should not be hard.
It should not be hard, but I like doing a lot.
Well, think about what we just did.
I mean, I know that. I mean, like.
I didn't say it had to be a professional information.
But I just like, I'm trying to, right, and then you want to improve, yeah.
Well, what did you come up with for epsilon?
L before. And if I get that, like, I don't know. It's less than much. I don't have a good.
Okay,
Yeah. It's just.
And then what?
Then it's like. What is this one? Yeah. Wow. No, like, you should, I'm fine.
Okay.
yeah.
And then I plug it in, and then I should be able to find what equality all I want, but I'm not getting that. Yeah. I found something that was like,
Yeah.
this is not working.
Wait, but what if L is not?
Do you want to use epsilon equals, let's say, L before? Okay.
A that is really L that is like three.
Why don't we draw a picture?
Yeah.
I'm always going to tell you what does AN look like? Where is actually not even AN look like? Where's L?
Then A that is minus L is L.
Why do you need that? You need it.
Like I said,
You need it, so let's say.
That's the absolute value sequence.
So, yeah.
We should work.
Yeah, so this is really a very good test of
I really should work out very long. Absolutely. Then it can also be in this group. Why is this annoying? There was a way to split Gallon into pod.
I'm not seeing a lot of pictures. I always have to draw a picture to think.
I don't see a lot of pictures.
Yeah. Not sure why you need it. Can we do it together? Maybe one more time. A little bit more. You got it. Let's say 5 minutes. I don't want to spend all class on this, but I think this is a really good example of the kind of thing that, this is a really good test for me to understand how fluent we're getting with this mechanism.
Like, you know, you can like split. Absolute I is less than something to like the 2 parts.
Yeah.
Maybe the same for greater than.
Yep.
And then like reverse that.
Um,
If I can do that. I don't know. if it-
shouldn't have to. Part of this is like, you know, an escape room.
Yeah,
And the tools that you have are the ones that you would see if we were looking on the right hand side. And it should be possible to put all those tools together.
It's a natural language proof is fine, right?
Natural language proof is perfectly fine. As long as you know how to convert that natural language proof into a form using the tools that we. I mean, what would you show me what you would like?
like. I need this and just.
This. You know, like I said, then like it's only right, bro.
No.
Fucking.
You think another way to do it?
Oh, we couldn't use this side. What?
Wait, I'll look for two, or like after that.
Yeah.
I feel like I'm doing that from the wrong side thing all the time. And I just,
You know.
Yeah, like what's.
what to prove it's certain, is there one thing you just less.
So try to do like things more.
Where's the other?
Don't say that.
Yeah, it's less.
It's always positive.
Plus three. Yeah. And
You can just say, yeah, it's also like I said.
So then we have
Yeah, you're close. So I should be able to.
Yeah.
Yes, somebody's using.
Okay, let me write down the part that I think everybody got so far. So what did you guys choose for epsilon? L over 2. L over 4 is fine also. So let's start the proof. First of all, we need the fact that absolute value of L is going to be positive. That's because of, let's call this have F0, is that L is positive. That's by apply, what was that called? Abs pos. But what's the condition of non-neg? Of non-zero. And how do we know that L is not zero? Because that's called LNE0, bless you. LNE0. Okay, so we know that L is non-zero, and then we can have F1, which is that not only is L strictly positive, but absolute value of L over 2. Over 4 would be fine as well. Let's just use over 2. And this is by bound. Okay, so what? All right, let's make a little bit more progress. So we want to specialize this A to L, the fact that we have this sequence, specialize A to L with epsilon replaced by L over 2, and the proof that L over 2 is strictly positive is F1. Okay, so now A to L says there exists an N, so that for all N greater than N, AN minus L is strictly less than L over 2, absolute value of L minus 2, right? Everybody with me so far? So that was kind of the easy part. And then, of course, the next thing is choose NHN using A to L, which makes HN equal to, for all little n greater than capital N, AN minus L is less than L over 2. So far it's been very easy. So we have this capital N. The goal still says, the goal is there exists some, we have this eventuality. There exists some capital N. Which capital N should we use? Or just capital N itself. We already have capital N, so just use it. Use capital N. So now what's happened is that the goal became for all n greater than n, AN is at least L over 2. And so now what? Intro little n HN. Okay, so we know HN is that little n is greater than or equal to n. And now what? Specialize, thank you. Specialize what? HN, H capital N, which is waiting for a little n, and it's waiting for a proof that little n is greater than capital N. So we've gotten ourselves down to HN now says that AN minus L is at most L over 2. And our goal is, is that AN is at least L over 2. I think most of you got this far, just mechanically. And now you actually have to have an idea. You have to figure out what to do with this. This is where I said I always have to draw a picture. I have these absolute value of ANs. Absolute value of AN, that's the object that we're thinking about. It's doing this. And it's approaching, well, I think it's approaching absolute value of L. In fact, that's the next thing we're going to prove, is that the absolute value of a sequence approaches the absolute value of L. But we don't know that yet. We can just sort of think about it, that this is getting closer and closer. And in fact, it's within after this point, capital N, all of the values are within epsilon of capital L, but that epsilon is L over 2. Right? So how do we say, well, that can't happen? This is the part, this is almost exactly the part in a natural language course where students say, and it's obvious, this can't happen, and then that's it. And as the instructor, you're supposed to go, what are you supposed to do with that? It is obvious, but how do you actually prove it? Just because you said it's obvious doesn't mean it actually is obvious to you and you know how to prove it. Daniel. Triangle inequality. That is absolutely essential. Triangle inequality for what?
Yeah, right.
This is where the skill comes in and the practice comes in. Suhas.
Yeah, so, well, actually, I think I had what I was saying.
Tell me what you start your calculation with.
I have absolute value of L over 2.
Okay.
And then if I triangle any, or you can rewrite it as absolute value of A of N plus L minus A.
Okay, I'm just going to write what you're telling me. Absolute value of L over 2 is what? Is equal to or?
And absolute value A of N plus L minus A.
A of L minus L?
A of N plus L minus A.
Plus L plus L minus A of N.
No, but the parentheses are on the last.
Why can't I undo? Here we go. The parentheses are on the last two. L minus A of N?
Yeah.
Okay, very good. Very good. That is the idea. There's a cleaner way to do that idea, which is think about what happens. So we know that this distance between A of N and L, which is here, this distance is less than epsilon over 2. So if A of L was down here, then it's actually this distance from L to 0 that would be too small. Let me say that again. If A of N, if this wasn't true, if A of N was actually less than L over 2, then it'd be down here. This distance would be too small because this distance is less than L over 2. And if this distance is also less than L over 2, then that distance can't be L.
Yeah.
That's the picture I want you to see in your mind. That's what takes practice to get really proficient at. So what you're doing is exactly right. You'll get there. You'll get through the algebra until you get there. And then the clean version is take the absolute value of L itself and write that L is the same thing as, well, I have an AN minus L. So maybe I want, all right, I'll just do it A minus, I'll do basically the same thing as what you did, except without the 1/2. L minus AN plus AN. That's ring. And then that same thing is less than or equal to L minus AN. I don't need the extra parentheses. That's by triangle inequality. And then this thing, absolute value of L minus AN, now we have to do our annoying thing that I should have just given you the theorem for. That's equal to that. And then negative AN minus L is equal to AN minus L. This is less than, bless you, is less than epsilon over 2. And now it's just linear arithmetic because, in natural language, the computer can just do the arithmetic for you. But in natural language, if I move this to the other side, and this is less than L over 2, then A of N is at least absolute value of L minus absolute value of AN minus L, which we can change to AN minus L after this operation. Everybody see that? And this is at most L over 2, which means this is at least L minus L over 2, which is L over 2. So it's basically what you were starting to do. Just for me, the idea is what's wrong if this inequality doesn't hold, if this AN is not less than or equal to L over 2, is that L is too small. L can't be too small. L is as big as it is. Does that make sense? Yeah, everybody got it? All right, why don't you hand in your papers to Joe, please? Give yourself a point. And I'm glad to see that this is still something that we need to spend some more time with. I wasn't sure if you guys would all get this instantly or if it's something we need some more practice in. But this is exactly what your homework is supposed to get you really, really good at, solving these kinds of goals. Let's give each of these things a name. What do you guys want to call this fact? We already have an F1, I guess. So let's call that F2. Let's call this F3. Let's call this F4 and this F5. And then linear arithmetic using all of these chains everything together. Does that make sense? Is everybody following along? Stop it.
The last step, you should absolute value of L minus L over 2 is absolute value of L.
This?
From there,
I'm missing an absolute value, of course.
oh. And then, because the absolute values are there.
This is just absolute value of L. I'm pulling out an absolute value of L, and I'm left with 1 minus a half.
Okay.
Does that make sense? Take a minute and look at what you wrote. I guess it's too late. You gave it to Joe already. But think about what you wrote and hopefully everybody got to this point. This point is just mechanical. And now you actually have to have an idea. And for me, the idea is to think about this picture. What would happen if AN is less than L over 2? Well, this distance is less than L over 2. And if that distance is also less than L over 2, you can't cover a distance of L. So it's a triangle inequality on L itself. Okay? Does that make sense? Let's do it. I'll take those, Joe. And you. And let's do it formally. Let's check if the computer agrees with our argument. How small can I make this? That's as small as I can make it. Okay. All right, so what's the proof? We start with have F0, which is that absolute value of L is positive by apply, oops, what happened here? Apply abs pos. I always want to say of non-neg or something. It's of non-zero. And what's the non-zero-ness? It's L any 0. Okay, so far so good. We have that absolute value of L is positive, and now have F1, which is that we can take half of that, and it'll still be positive, and that's by bound. And now we're going to specialize. I'm just following our instructions here. Specialize A to L with epsilon replaced by L over 2, and the fact that L over 2 is positive being F1. Okay, so we know there exists some capital N, so I'm going to choose capital N HN using A to L. This is all very familiar to us, and then I'm going to use that capital N. All right, and I'll intro little n HN, and then I'll specialize H capital N to little n HN. And now we have that AN minus L is less than L over 2. All of that was completely mechanical. It should not have taken any thought. All of you should have done that in the first 30 seconds. Now it's like, what do I do? And the key idea is right here. So we're going to set this F2. Can I get rid of this? Go away? No, I can't. Okay. Let's have F2, which is the fact that the absolute value of L is the absolute value of L minus A little n plus A little n, and that's just by ring. Okay, and then this thing have F3. This thing is less than or equal to the same thing, but with absolute values here and here. And that's by apply abs add, the triangle inequality. Now this thing, we got to do our annoying little, maybe I will give you that theorem so we don't have to do it anymore. We do it so often, I should have just given you that theorem name. This is equal to negative AL, AN minus L. I thought I was doing something right, but obviously not, because we keep doing this and it's annoying. We shouldn't have to do things that are annoying, and then have F5, which is that this thing is equal to the same thing without a minus sign, and that's by apply abs neg. All right, So AN is lower bounded by something that's equal to L, and this difference, which is equal to that, is less than L over 2, and L minus L over 2 is L over 2. And so that's a lower bound for AN. And so everything else should be a matter of chaining linear arithmetic of H capital N with F2, F3, F4, and F5. Booyakasha. You like it? Is it clear now? Did you have a moment there to feel the struggle of what's working and what's not working and see what's going on? There we go. And see where the key idea is. For me, the key idea is F2. Everything else is mechanical. F2 is the idea. It's absolute value of L that gets too small if the goal is wrong. Okay. Great. Any questions? Next. I hope we'll have time for 2 more. All right. Abs lim. So if you have a sequence AN and an L and A goes to L, and you have some other sequence B so that B is the absolute value of A, prove that B converges to the absolute value of L. There's one theorem that I'll quote in this proof that I'll add as a homework, which is the Lipschitz property of the absolute value. And I'll explain Lipschitz property is that let's go back to natural language. Let's drop this over here. Whoops, too far. Over there, and here we are. Next theorem. This theorem, did it have a name? It does have a name, abs lim. Abs lim is the name of the theorem, and it says A goes to L, and B is equal to the absolute value of A, then B goes to L. Okay, this has a name. This is called A to L. B is absolute value of A is called B eq abs A. I could have given a much better, it should just be called HB or something. Sorry. B eq abs A is the name of that. And then this is our goal, that B goes to absolute value. Okay. And I'll get to the theorem name that we need when we need it. What's the idea? We're trying to prove B goes to absolute value of L. We're gonna get to the triangle inequality later, but how do we start the proof? Intro, let epsilon be given. Yeah, let epsilon be given. That's called intro epsilon H epsilon. Okay, this inequality is H epsilon. Then what? Yeah, there is a way to choose right away, but let's do it in 2 steps. So we'll specialize A to L to this epsilon and the fact that this epsilon is positive. Okay, so now A to L says there exists an N. So Daniel, choose that N and Hn using A to L. So now Hn, what does Hn say? Okay, very good. And what is the goal at this point? Keep track. There exists an N. Yeah, the goal, let epsilon be given, we need to give it a capital N. Which capital N should we use? Capital N itself. Yeah, use capital N. I guess we should have thought about this in natural language first. Sorry, I assumed it was obvious, but maybe it isn't obvious. If your sequence is bouncing around doing whatever it's doing, maybe it's positive, maybe it's negative. Well, absolute value of L, the fact that it's going to the absolute value of the fact that the sequence is going L. Why am I drawing in my mind instead of on paper? The fact that a sequence is doing whatever it's doing, but eventually it's got to get to L. So even if L is negative, the sequence is getting closer and closer to L. So when I take the absolute value of the sequence, so this is the sequence AN, and if I look at the sequence BN, which is the absolute value, BN does exactly the same thing, and then instead of going down, it goes up. And then it does, I'm trying to copy this, and then it comes over here, and then it goes over there, and the absolute value of L is over here. Okay, so that's what BN is doing. And so for AN to be within epsilon of L, wherever L is, that's also the condition for BN to be within epsilon of L. Hopefully you have that intuition. You don't have to do anything with the epsilons, you don't have to do anything with the n's. Okay, does that make sense? So use n, so the goal becomes, at this point, the goal says, for all little n greater than n, Bn minus L is less, minus absolute value of L is less than epsilon. And so what should we do? Yeah, intro. Yeah, let's write it in natural language. Let little n greater than be given. Be given. And we'll call this hypothesis HN. Okay, now what? We have a little n and specialize specialize H capital N to little n and a proof that little n is greater than capital N. Okay, so at this point, what we have is the following. We have Hn says what? An minus L is less than epsilon, and our goal is, yeah, not yet. Let's do one more thing to get that absolute value. So specialize something else. What was it called? This B, the fact that B is equal to the absolute value of A. Let's get that into the, it's going to be a rewrite once we specialize it. You can do them, you can do them both in one fell swoop, but I'm trying to, for pedagogical reasons, slow us down. So specialize this god-awful B eq A abs A thing, which should just be called HB or something, to little n, and then rewrite B eq abs A. And now the goal will say, yes, now I can stick in absolute value of A instead of a B here, minus absolute value of L is less than epsilon. Okay, so now we need a little conversation about Lipschitz functions. So this is a definition or something. This is just an aside. A function f is called Lipschitz if it satisfies this property, f of x minus f of y is less than some constant times x minus y. Okay, so if a function is like, doesn't change by more than a constant multiple of the variables changing. Okay, and you will prove an exercise that will follow this is that the absolute value function is Lipschitz. And the absolute value function is Lipschitz with constant with c equals 1. With c equals 1. So maybe you've never thought about the absolute value function, but the graph of the absolute value function is this. So yes, if you change, the only question is what happens around here. But yes, if you change from x to y, the value of f changes by no more than 1 times x times y. And in fact, can sometimes get smaller. It's a line. It's basically a line with slope 1. Okay, so lines are Lipschitz. And the absolute value function is basically a line, and there's a little place where you have to be a little bit careful. Okay, so I'm going to make that an exercise that will test your case splitting with absolute values. But the upshot is that we have a theorem called Abs-Lipschitz. That's our new theorem. Where was it? Here. We have a new theorem called Abs-Lipschitz, which is that the absolute value is Lipschitz. Okay, so abs, I think it's lowercase abs, Lipschitz says that the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y. And so what would we like to call at this point? Let's call this a have f. That with x and y replaced by an minus absolute value of L is at most an minus L. Okay, and this is going to be by apply Abs-Lipschitz. Does that make sense? Now here's one really annoying lean thing. Remember how you can't have a space after the absolute value? You can't have an absolute value after an absolute value. So what should we do? parentheses. Okay, we're going to put a parenthesis there, and then everything will be okay. Sorry, I didn't make the syntax. Let's do it. Okay, whatever, apply nothing. Just give me the theorem back. All right, so this should be pretty easy. Let epsilon be given. So intro epsilon h epsilon. Great, we have our epsilon, we have that it's positive. Now specialize a to L, specialize a to L with this epsilon and h epsilon. Now we're going to choose, this says there exists some n, so choose it. Choose capital N using a to L. And then once we have that capital N, you got it. If you got it, use it. Yeah, use it. Okay, and then intro NHN. Again, this is just completely mechanical at this point. And then we're going to specialize HN to NHN. Okay, great. So now I'm up to this point. And then also we want to record the fact that it's that we can rewrite this B of N. We're doing one extra step that we technically don't need to, but pedagogically is good. Specialize that to N. So that particular value of N, we have B of N is equal to A of N. Now we can rewrite this. B eq abs A. Beautiful. All right. So we need to show that the absolute value of A of N is within epsilon of the absolute value of L, knowing that if you didn't have those absolute values, just A N itself minus L is within epsilon. This is exactly where the Lipschitz property comes in. So have F right here, so we can stare at it. F is that now if here's the funny thing, if I copy what it said, Lean won't take it. So I have to put the extra parentheses because it hates absolute values, is less than or equal to the same thing without the absolute values. And that's by apply abs Lipschitz. Yes. And now, Linnereth. Linnereth using what? So this is less than that by F, and then that is less than epsilon by HN. Boom. Cool. So if you have a sequence, converges to L, its absolute value converges to the absolute value of L. Now we're ready for a big boss. And I fear we might not have time to do it. Let's just reload. Here's one of the big bosses, and this will be the big boss of the section. Maybe we can do it. We can certainly spend 5 minutes thinking about how to do it. And maybe we'll have to pick up the proof next time. If you have a sequence AN that converges to L, and L is non-zero, then the sequence 1 over AN, where does that converge? To 1 over L. Okay, let's do the mechanical bits. Let's do them quickly. What's the first part? Intro, give me an epsilon, H epsilon. Maybe we can do this we have 6 minutes. I think we can do it. If we follow, okay, then we have that epsilon. Now what? Specialize. This would be very cool if we could get this in that amount of time. Specialize. Yeah, okay. Let's do this move and then we'll figure out what's wrong with this move. Okay, we might need more precision than the precision that we have allowed ourselves on epsilon. We've seen that sometimes we need epsilon over 2, sometimes we need something much more. Let's just pretend that we knew what the right value of epsilon to put in here. We'll see in a second that that's not quite the right epsilon. Okay, so let's say we have that precision. So now choose capital N, HN using A to L. Which value of epsilon it will exactly be the key, that's right. And then use that capital N. And now intro little n HN. And now specialize what? HN to little n HN. Okay, so we know that AN is within epsilon of L. Let's rewrite BN. Okay, so specialize. What's that? You see it? B eq inv A to N. And now we can rewrite. I should just call this HB. I'm trying to be too, whatever. All right. Can we prove that 1 over AN minus 1 over L is within epsilon if AN minus L is less than epsilon? Okay, let's see what we actually have to do. Oh, okay, at least it crashed, but I can still see what we got down to. So let's write this out. So theorem, this is called invlim, invlim, which is that A goes to L and L is not equal to 0, implies 1 over A should go to 1 over L. Okay, and let's say we know that, so we got as far as, the way you should really start at the end is say you know that A minus L is less than delta, and I don't know yet what delta needs to be. And we want to so our goal is that 1 over AN minus 1 over L is less than epsilon. And this is unknown. Let's see what we can do. So we know that 1 over AN minus 1 over L is equal to, if I cross multiply, I get an L minus AN over ANL. By the way, there's something called, there's a new theorem that we need access to. Okay, I'm just gonna, as a human being, turn this around, and then this is gonna be over AN, and that's gonna be L. And the fact that this is true, there's something called abs div. Just like we had abs mul, there's also abs div, which is that the absolute value, I'll write it here, the absolute value of x over y is equal to the absolute value of x over the absolute value of y. Okay, that's one stupid thing that should be in bound and isn't. Okay, so far so good? Here's the problem. I want this to be less than epsilon. First of all, I don't have control on this. Maybe A of n is equal to 0. What are we supposed to do here? Actually, maybe A of n is really, really small. If it's equal to 0, then dividing by 0 gives you 0. But maybe A of n is really, really small. So I know that A of n minus L is within delta. So that's what's making this small, but this might be small. Is there some way to make sure that eventually, once we go far enough out, AN of L, absolute value of AN can't be too small? Sean?
The previous.
Well, exactly what we just proved. The thing that we just proved is that if you go to L, the two before, if your limit is L and L is not 0, then you'll always be at least, you'll eventually be, after a certain point, you'll be at least L over 2. Okay, so we're not going to have time we're going to have to pick this up next time. So next time, we'll finish this level. The idea is make little n so large that absolute value of AN is at least L over 2. Now we have a concrete upper bound on everything that's going on because I have a lower bound on AN that gives me an upper bound on 1 over AN, and then we'll maybe be able to make a good choice for epsilon. All right.